Derve. That is a common form of greeting in the Finnish language. So far, in our quest for the proof of the Coarea formula, the one that you see on the screen, we have checked the following. We have talked about an implicit function theorem, which allows to locally rearrange the fibers of the Lipschitz function to become honestly vertical copies, hyperplanes of dimension m minus n with the use of a C1 diffeomorphism G. Then we talked about why the coarea factor has to be what it is, and also we discussed towards the end of that video that we gave a formula for how the coarea factor of FOG inverse is related to that of the original f, because we want to do the computations in the domain of FOG inverse, where we can apply Fubini's theorem, but we need to know how the coarea factor transforms under that diffeomorphism G. And that we have computed in that video. Rather, we have left it as an exercise, but there's a lot in that video, so you can do it on your own. In that video, we also discussed that to prove the full version of the coarea formula, it is enough to look at the functions g that are characteristic functions of measurable sets A. In that case, the formula reads just as follows. The inner integral is computed and it's just the hm minus n measure of this set, because we know how to integrate characteristic functions. We need the two more tools to complete the proof of the Coarea formula. My last video will be a summary of everything and how all of them fit together into a full proof. Don't worry if it becomes too much. And that one of the two tools that we discussed, one of them is the Coarea Inequality that I talk about today. The other one is Weak-Sard theorem, which is kind of an advanced version of, again, the Coarea Inequality, and that takes care of the set where rank of derivative is not n. Okay, there is a very important question which we have to attack right now, and that is, why on earth would we want to prove a Coarea inequality if we are going to prove a Coarea equality or a Coarea formula? And there are two reasons. Number one, Coarea inequality, as you will see, holds for Lipschitz maps between arbitrary metric spaces, so it's way more general than just for maps between Euclidean spaces. Second reason is that to deal with null sets in our domain, even in the Euclidean case, we don't have any of the tools we have discussed this far, because you will have, for example, a null set where your function is not even differentiable, so you cannot even talk about approximating by linear maps or anything like that. So two reasons why we need a Coarea inequality. Okay, let's get to the business. The general version for maps between arbitrary metric spaces reads as follows. So let y and x be any metric spaces. You can take a singleton, a finite metric space, an infinite one, a huge one, a Hilbert space, whatever you can imagine, and fix any pair of numbers as real numbers s bigger than t. Then for any Lipschitz map f from y into x, and any subset of the domain, we have the following. So you want to integrate a quantity which is very similar to what we have in the Coarea formula. So s minus t, that makes sense because s is bigger. F inverse of the fibers intersecting with A, and of course the fibers above the point from the metric space X. And we kind of think that X is t-dimensional and Y is s-dimensional, although they are not in the assumptions. So, but this is the easier way to interpret this. This function may not be ht integrable or measurable even, so we use the notion of upper integral. So this is being integrated over the metric space X. I have a complete playlist, 10 videos on Hausdorff measures, how they are defined, how they make sense on any metric space. And then once you have the Hausdorff measure, you can of course integrate. Integration is nothing other than measure theory. So once you have a measure, you can always talk about integrals. And the upper integral, a quick maybe recall that upper integral of a function is infimum of the usual integrals of measurable functions. So integral of measurable functions where the infimum is over all phi that are so measurable and bigger than or equal to f. And if f itself is measurable, then you can take phi to be f, and this becomes, so integral of a star is just the integral if whatever is being integrated is measurable. But in this general context, this may fail to be measurable. Therefore, we need the upper integral. But the claim of the theorem is that this is less than or equal to Lipschitz constant of f to power t times the measure of the domain. So here A. And then there are some constants that are needed. And those constants are the ones that we use in the definition of Hausdorff measure. Those dimensional constants which make Hausdorff measure k to be equal to the Lebesgue measure k when k is an integer, positive integer. So we need those correcting factors to make this work. And so omega t, omega s, minus t, and then here omega s. Okay, so that is the end of the theorem. An amazing theorem, again in this generality, proven by Federer, but simpler versions were proved by Eilenberg. So this is also very famously known as Heidenberg's inequality. So either Coarea inequality or Eilenberg's inequality. Both are famous names for this. The proof of this theorem is quite difficult and deep. Needs a lot of tools and machinery. But when your target space X is the Euclidean space Rn, and the measure, the t, you take t to be the same as the dimension of that space, then there is a simpler proof that I'm actually going to do right now. So the simpler version is that y is arbitrary, s bigger than or equal to n, and n is natural number, f from y into Rn is Lipschitz, and A is a subset of Y. Okay. So let's directly begin the proof. So the statement is just as before, except that T is now this N, and X is the metric space Rn. We need to show that this upper integral of h s minus n f inverse of z intersected with a dln, because hn agrees with ln now, of z integrated over Rn is less than or equal to omega s minus n, omega n, omega s times Lipschitz constant to power n. So let's write L to be the Lipschitz constant of f for simplicity. And then this will be hs measure of the set A that we start with. So we need to prove this. Okay, where can we start? Because there isn't much we can do, we have to go back to definitions. And what were definitions of the Hausdorff measure? So suppose, we shall assume that this hs of A is finite. Also, we assume that this is not zero, because then f is constant function and everything is simple. And if L is positive and if hs A is infinity, then this side becomes infinity. There is nothing to be proven, so we can assume this. Okay. By definition then, so how are Hausdorff measures defined? First, we define the Hausdorff content, and then so for any epsilon positive, okay, so there exists delta positive such that hs delta of A, which is always, so remember this is always less than or equal to hs delta. As delta goes to 0, these increase to the Hausdorff measure, and but so because limit of this hs delta equals this, and this is a finite value, therefore when delta is small enough, this will be bigger than hs of A minus epsilon. That's just by definition of hs A. Now we apply definition of hs delta of A. So there exists a covering of my set by subsets EI, a countable or finite covering, such that diameter of each EI is less than or equal to delta, and okay, so the summation of diameters diameter of EI, so these are used to compute the s-dimensional Hausdorff content, so this to power s, so I from 1 to infinity, or maybe finitely many, so but remember that, okay, remember that we need the constants. So here the constants will be omega s, and then you divide the diameter by 2 first, and then raised to power s. So this would be 2 to negative s and omega s. So summation I of this quantity can be very close to h okay, I have to be careful with the notation here. So this will be h s delta of a plus epsilon. Okay, remember this infimum of all such quantities, the infimum of all such quantities equals this quantity. So when you add epsilon to it, one particular element must be less than this quantity. So that's definition of infimums. So there is a particular selection of delta coverings of the set A which satisfies this. Now let's see what is the situation like. So we are in space Y. We have our set A sitting here, and now we have these sets EI. They don't have to be circles, but it's easier to draw them like that. So these are EIs, and the diameter of each EI is less than or equal to delta, and this summation of the s power of their diameters is approximating the hs delta, the Hausdorff content of A, which in turn is approximating the hsa of A. Now, the map F, of course, takes these to the space X, which is Rn. And each EI gets mapped to some F of EI here. Okay. Something like that. Okay, now let's fix Z in the target space Rn. Then F inverse of Z intersected with A, it could have parts here and here, but we don't care about, so this is F inverse of 1z. The part that is intersected with A is contained in this union of EIs. Well, EIs cover all of A. In particular, they cover any subset of that. So this is a not efficient way of covering just the fiber, as this picture also illustrates. So here you can say only certain EIs, so relevant ones, and I'm gonna then show you exactly which ones are relevant. So EI is relevant for this covering, so EI contributes to covering F inverse of Z intersected with A if and only if there exists some point in this which is also in EI, and that would mean that Z belongs to image of EI. There is some X in EI which belongs to this pre-image, which means f of x equals z. So z belongs to f of EI because that x is from EI. Okay, so then this becomes instead of relevant EI, so this will be those i's such that z belongs to f of EI. Now this here is a delta covering of this set. And therefore I can estimate the n-dimensional Hausdorff content, delta content of that set. Sorry, this S minus n, I need to compute this quantity. So I can estimate this from above. Remember, this is infimum of over all such coverings of such quantities. So to compute S minus n dimensional Hausdorff content, you have this correction constant, this always there too, and then this will be diameter of EI to power S minus n, and this will be again those relevant i's, I such that z belongs to f of EI. But then there is a clever way of writing this summation, and I can do summation over all of i's, and for this condition that z belong to f EI, I use the idea of the characteristic function. So I'm adding now everything S minus n, but now I want to include some quantity which exactly counts in those with this condition and removes those that do not satisfy this. And that quantity is characteristic function of f of EI applied to z. So in this summation, in effect, those will be counted for which this quantity equals 1. And that is exactly when z belongs to f of EI. And if that condition is not satisfied, that will not be counted in. So I can remove this because the quantity I am interested in, the inequality is this one. That this function is less than that. And this is for every z. So I have a function less than another function. A module of some measurability issues. So I leave it as an exercise here that we could start with closed EI. Actually, this is not an exercise. This is included in the playlist on Hausdorff measures. In a video, I proved that in the definition of Hausdorff measure, you can always restrict to coverings only by closed sets or only by open sets. So in this case, I only cover by closed sets, and because their diameter is less than delta, they are compact sets. So therefore, these FEIs become compact sets, and as a result, this becomes a measurable function. And then therefore, this summation here is a summation of measurable functions. Therefore, it is itself is measurable. So the right-hand side is a measurable function. And these are functions on Rn, and by measurability we mean Ln measurable, because z is taken from Rn. So we can estimate the upper integral of this function S minus n delta f inverse of a singleton intersected with a dln over Rn by this integral of this function here. What is the integral of this function? It may look a nasty function, but these are just numbers, constants, and these are characteristic functions. An integral of a measurable characteristic function of a measurable set is just a measure of that set. So this will be summation. So what were the constants here? So omega s minus n, 2 to power s minus n. diameter of EI to the power s minus n. This is just a constant number here. And then Lebesgue measure of FEI. So Lebesgue measure of F of EI. And here comes the key moment where we use the isodiametric inequality. And that is why the proof of the Coarea inequality is so much easier when target space is a Euclidean space and we are also talking about the Hausdorff measure of that same dimension. Because that is the only case where we have a simple isodiametric inequality. So I will just copy this, and in the Hausdorff measure playlist I also have a separate video on isodiametric inequality, which, by the way, is the reason why Lebesgue measure agrees with the Hausdorff measure on Rn. So this is just the number. The isodiametric inequality says that Lebesgue measure of a set will be no bigger than, okay, so as if it was the ball of same diameter. So the ball of same diameter, so the ball of same diameter as FEI has diameter of FVI divided by 2. That is the radius of the ball. And the Lebesgue measure of the ball of this radius is omega n, the unit size of the unit ball, and then to power n. So that is the isodiametric inequality. Now this equals, let me put all the constants up front, omega n, and this 2 to power, this will add up to power negative s, because I have 2 to negative n from here. Sorry, not yet. So s minus n, 2 to power minus n. Well, I was right. Okay, sorry about that. And this will be diameter of EI to power s minus n. Okay, now I have a simple estimate on diameter of image of a Lipschitz map. A Lipschitz function increases the diameter by no bigger than the Lipschitz constant times the diameter of the domain. So this will be that to power n. Okay, we are almost done, actually completely done. This just needs a rearrangement. What I do here, I have this number, I divide by omega s. So inside the summation, I multiply by that to get rid of that. Then I have 2 to negative s. I also put this Lipschitz constant to power n here. And then I will have diameter of EIs to the power s. Because I have plus n here, minus n here, cancels out, and I get this. But guess what? This quantity was chosen. This is estimating the s-dimensional Hausdorff measure. And the choice of EIs were such that we had this, and we had this. When you put them together, this becomes less than or equal to, I cannot do anything about these constants. I have to live with them, so Lipschitz of f to power n. But what is living here, this is the Hausdorff measure, s measure of A, plus maybe 2 epsilon, because I had epsilon error in each step. So I have my Coarea inequality. Let me show show you how. So I have this less than this. And now let epsilon go to 0, because that was arbitrary. And the strict inequality, of course, becomes equality, possibly equality. Okay, so that is a showcase of the basic ideas behind the proof of the Coarea inequality. Even in the metric, more general case, you follow a similar path, but then you have to work a lot harder to get past this step without the full isodiametric inequality. What ends up being the case is that locally, you're talking about delta scale here, and it turns out that locally there is some version of an isodiametric inequality on any metric space, but those are not suitable for this presentation, at least, to get into. Okay, consequences. Okay, now that we have went through this pain, what are the fruits of this effort? Suppose A subset of Rm and Hm or Lm here of A is 0. So this is my subspace Y. If F from Rm into Rn is Lipschitz, then integral over Rn Hm minus n F inverse of Z intersected with A, the Ln of Z equals 0. In other words, for Ln almost every Z in Rn, the preimage has 0 m minus n dimensional measure. And that is not a trivial thing. I once mentioned this. Suppose you are talking about the simplest case of the map from R2 into R1, which is just a projection. Okay, so this becomes just pi of x. So the fibers are the intersections of vertical R1s with the space with the set A. If A is a null set, that means it is L2 null set. It has no two-dimensional volume. And the claim is here that for almost every point you pick here, the intersection with that set will have 0 one-dimensional measure. And that is a consequence of Fubini's theorem, and there is no other way of getting that. Let me draw a better picture to illustrate what can happen. Okay, so my set A is going to be, say, a plus sign. And maybe just to have more fun, add some more vertical lines. So this A is a null set. Its projection onto R1 is actually all of R, because this line goes to infinity. So because you have a null set in R2, doesn't mean its projection is also small, because you're going into a smaller dimensional space. So its image of this L2 null set is all of R1, the biggest that can be. And also we see that for some x in R1, the preimage, which is fiber above x intersected with A, does have positive L1 measure. Namely here, these are those particular x's which can happen. And you can have more. So for example, you can have countably many of these. You can also have uncountably many x's where this happens, but this theorem says that you cannot have a positive set of x's where this happens. So if A is L2 0, then the set of x's for which the fiber has positive 1 measure should be a negligible set. Otherwise, by Fubini, you will get a positive measure for the set A. So here you could take a counter set and then multiply it by R1. So that is like that case, that you can have even uncountably many x's where this happens. And also this illustrates that you cannot get any result better than this. Only you get almost every preimage. So in the projection case of F, this is Fubini's theorem, but for Lipschitz F, you need the Coarea inequality. So the proof of this is, of course, there was this constant, and then there was the measure of the set A. So this is 0, and done. That's the proof. So that is the most important corollary of the Coarea inequality that we will need. But there is a second consequence of Coarea inequality, and that is to an important question of measurability. So in all of the repetitions of the Coarea inequality, what I have written is that this quantity, okay, intersected with A, dln of z equals integral of the Coarea factor, whatever, right? So in this integral, in writing this integral, we have been implicitly claiming that in fact the integrand is actually measurable. So whenever you write an integral, you should always ask, is it a measurable function that I'm integrating? It's a non-negative function, so there's no question of integrability like plus infinity minus infinity case. So it's only a question of measurability. So we have been implying that this is indeed measurable. So that this function, z going to hmn, whatever is inside the integral, is measurable. This is in fact true if A is Lm measurable. If you begin with the measurable set in the domain, this is always measurable. Its proof requires this corollary 1 above, that for null set almost every fiber has 0 measure. So even to state the Coarea formula, to prove that the function is indeed measurable and you can integrate it, you need the Coarea inequality right there. So that is one use of it, and the other use of this is of course to null sets, for example, where the function f will not even be measurable. I don't want to give a full proof of this fact, but a quick sketch is that if A equals K is compact, then using open coverings, open like coverings by sets of diameter less than delta, similar to what we did above, we can prove that Z going to H mn F inverse of Z intersection with K is measurable. In fact, that it is Borel even. The idea is that if you're here and you have an open covering, so if you have Z and the pre-image of Z intersected with K is somewhere like this, it's covered by these open balls, by these, not balls, just open sets. The claim is that if you pick another Z pretty close to it, the pre-image again will be covered by the same collection of balls, so that you can use the summation of their diameters not only to estimate H m minus n for Z, but also for Z prime as well. The same set of open sets also are sufficient to cover F inverse of other points, provided they are nearby. And compact, it's just a compactness argument. It's a beautiful exercise in basic topology. So this way you prove it for compact sets. Then for arbitrary A, measurable A, if it's not compact, it's just measurable, we write A as a union of compact sets plus a null set. And then this quantity is actually additive, so this F inverse Z intersection with A, its measure equals the summation of intersections with Ki's and then intersection with N. From the compact case, we know that the summation over I will be measurable as a summation of measurable functions. And now the Coarea inequality says, don't even worry about this part, because almost everywhere this will be a zero function. So let's write it out. So F inverse of Z intersection with A will be summation. You can take Ki's to be disjoint, for example. Minus A F inverse of Z intersection with Ki. So these are measurable functions, each one. So the summation is plus H m minus n F inverse of Z intersection with N. But now the Coarea inequality says that this is an almost everywhere zero function. And a function that is zero almost everywhere is definitely measurable. So you get measurability of that. Okay, so going back up to the very beginning, we now have confirmed yet another step toward the proof of the Coarea formula. So the only one left, and the topic of my next video will be some modification of this Coarea inequality proof to talk about the critical set of the function f, the set where its derivative does not have full rank. And that will bring us to almost full proof. And in the final video, I will again wrap them all up together. Thanks for watching today as well, and please subscribe if you haven't. That makes a difference on this end, even though if it may not make any difference on your end. See you in my next video.